Hello everyone, this is Edward Doolittle. I am going to give a lecture here on GCD of two numbers. Coronavirus edition. So this should be review for us, but I thought it would be a good idea to pick up a little bit before we left off so that we'll be prepared for new material soon. So for this exercise here, I want to calculate the greatest common divisor of 12 and 18. And I'm going to do that by four methods. So method one is list all divisors, find common divisors, and find the greatest common divisor. And so that is consistent with the meaning of greatest common divisor, so it should be easy for us to understand. So let's find all divisors of 12. So in order to find all divisors of 12, we are going to factor 12 into a prime factorization. So I note that 12 is 4 times 3. 4 can be broken down into 2 times 2. Those are both primes. 3 is also a prime. So I can finally rewrite 12 as 2 to the power 2 times 3 to the power 1. Now, armed with this factorization of 12 into prime factors, I can now write a little table of powers of 2 down the left side of the table. I go up to 2 to the power 2, but I start at 2 to the power 0. Along the top of the table, I'm going to go 3 to the power 0, 3 to the power 1. That's going to give me 6 cells in the table. The products are 1, 2, 4, 3, 6, and 12. So that means the divisors of 12 are, in order, 1, 2, 3, 4, 6, and 12. I'm going to do the same thing for 18. So I need to break 18 down into its prime factorization. 2 times 9. 9 is 3 times 3. And I circle the places where I stop. I'm going to have to repair this a little bit. Sorry. There we go. So 18 can be written as 2 to the power 1 times 3 to the power 2. There's 1, 2, and 2 3s. So my table for 18 is going to look like this. And again, there'll be 6 cells. This time it's 2 by 3. 1, 2, 3, 6, 9, 18. So the divisors of 18 in order are 1, 2, 3, 6, 9, and 18. Now, if you recall from our previous page, the divisors of 12 are 1, 2, 3, 4, 6, and 12. Now that we have lists of divisors, we can find the common divisors. I'm going to underline them. 1 is common to both lists. 2 is common to both lists. 3 is, and 6 is. Finally, to find the greatest common divisor, I just find the largest number that I've underlined In that case, that would be 6. So the GCD of 12 and 18 is 6. All right, so that's method 1. List all divisors. Now you can see it's fairly long. We will try to find ways to speed this up. So first thing I'm going to try is method 2. Just using the factorizations. So 12 has a factorization of 2 to the power 2 times 3 to the power 1. 18 has a factorization of 2 to the power 1 times 3 to the power 2. And now, just from that, we can get the GCD. I take the minimum of the numbers in each column. So 2 to the power 1 is the minimum in the first column, and 3 to the power 1 is the minimum in the second column. Now, 2 to the power 1 is exactly 2. 3 to the power 1 is 3. 2 times 3 is 6. So you see, once we have the factorization of the two numbers, then we can quickly find the GCD without going through all of the effort of constructing the tables of factors. So that saves us a considerable amount of time. However, these factor trees, making the factor trees, can be very difficult for large numbers. It can consume a lot of time. So we're going to look for another method. This one is due to Euclid. Called the Euclidean algorithm. It can be found in Euclid's Elements. No one is really sure if Euclid invented it or if he borrowed it from somebody else, but it's in the absence of any information to the contrary, it's attributed to Euclid, called the Euclidean algorithm. And in this method, we're going to use subtraction. So the idea is to find the GCD of two numbers. I subtract the larger minus the smaller, and I replace the larger with the difference. So I'm going to get here 12 and 6. I'm going to do the same thing again. Larger minus smaller. Replace the larger with the difference. Now, there's no clear larger number, but I'm going to take, say, the number I've been working on and just keep working on it. So the larger minus the smaller in this case is the same number minus the same number. 6 minus 6, I'm going to be left with 0. And the rule is if I have a GCD of a whole bunch of zeros or any number of zeros and a non-zero number, the result is always the non-zero number. So that is the Euclidean algorithm using subtraction. Finally, fourth method is an acceleration of the Euclidean algorithm. Oops, I should call this method 4. Euclidean algorithm division. So if you remember, division is multiple subtraction, so I can replace multiple subtractions with a single division, and that is the source of the acceleration that I obtain when I do the Euclidean algorithm with division. So let's check it out here. In this case, what I'm going to do is take the larger number, I'm going to divide by the smaller number, goes in just once. Difference is 6. I use this remainder, sorry, not the difference, but the remainder is 6. This remainder I use in place of the larger number. So now this is hardly any different from what we saw on the previous page with the subtraction version of the Euclidean algorithm. But the second step will go faster. So here I take the larger number, I divide by the smaller number. I find it goes in twice with a remainder of 0. I replace this larger number with its remainder, and that tells me that GCD is 0, 6, and again GCD of 0 and any number is that other number, 6. Notice that what I have done here is skipped over 2 steps. Well, skipped over 1 step. So I had, if you recall, the subtraction version had this extra line. And that is what we're eliminating by using division. So here I skipped directly from 12.6 to 0.6 without going through 6.6. This quotient here, this is the number of steps. Taken at once. So I've done 2 steps at once, and that has accelerated the Euclidean algorithm for me. So the acceleration isn't dramatic here. It still took us how many steps? 2 steps to get the answer, whereas if we had used subtraction, it would have been 3 steps. That is a small difference, but with some numbers, sometimes you can get enormous acceleration. Not always, but sometimes you can. All right, so that is a review of the Euclidean algorithm in 4 different methods. We have obtained that the GCD of 12 and 18 is 6.